Understanding how a resistor affects the flow of current in the circuit is a little bit like understanding capacitance. So let's take a look at our simple circuit with just a resistor and some source of potential difference, a DC power supply. If I could have my DC power supply set to some small potential difference, that generates a small electric field in my conductive wire, and all the charges feel a small force causing them to move. But there's a resistor in the way, and that small force isn't going to push too many charges through the resistor. So if I have a small potential difference set, I'm only going to get a small flow of charge through that resistor. Now I'm going to crank up my potential difference a little bit, and the electric field increases in strength, and the charges feel a bigger force, and more of them are going to push their way through that resistor. I'm going to get a bigger current to flow. And yes, I realize I'm mixing up my dependent and independent variables here, but I think it makes the point a little cleaner if I do it this way. Now I'm going to crank that voltage up a little bit more, generate a stronger electric field. The forces feel a bigger push. More get pushed through that resistor and a bigger current flows. You see where I'm going with this. And I keep doing that, and I get something that looks like this. This relationship tells us that the potential difference across our resistor is proportional to the current. And we like to write this as an equality, so we put our proportionality constant here. What is the proportionality constant? The slope of that line. We call that the resistance of our resistor. V equals IR. That's Ohm's law. And any device that obeys Ohm's law is said to be an ohmic device. Not all resistors have this nice linear relationship. This is the circuit from the last video. Let's take a look at how we can use Ohm's law to figure out some of the currents in these resistors. We found in the last video the potential difference across resistor 1 is 3 volts, and the potential difference across resistor 2 is 6 volts. So let's let resistor 1 be 10 ohms and resistor 2 be 12 ohms. If that's the case, we can use Ohm's law. The potential difference across resistor 1 is equal to the current in resistor 1 times its resistance. We know the delta V, and we know the resistance. The current through resistor 1 has to be 0.3 amps. We can do the same thing for resistor 2. The potential difference across resistor 2 is the current through resistor 2 multiplied by its resistance. We know there's a 6 volt potential difference across that resistor, and we know its resistance is 12 ohms. So the current through resistor 2 must be 0.5 amps. We've got 0.3 amps coming in from R1 into this junction. We've got 0.5 amps going out of that junction towards R2. So what must be coming up the middle path? 0.2 amps. That makes up the difference. I'll call that I3. So this 0.5 amps from R2 works its way down this side and across the bottom, and then it gets to that junction, and part of the current says, I'm going to take the fork on the right and go up through the middle. 0.2 amps takes that path. And part of the current says, I'm going to take the fork on the left and I'm going to go around and up through the 9-volt battery. 0.3 amps takes that path. And they meet up again on the other side. Now let's take a look at the second circuit from the last video. Here, we knew that we had a 15-volt potential rise going up through those two batteries. Then we come down through R1 and then through R2. Remember, potential rises and drops, they're like elevation changes on a hiking trail. If you start out over here at level 0, sea level, and you go up 6 volts, you're at some new higher elevation now. And then you go up 9 volts, you're way up at a much higher elevation. And then you come down through that first resistor to some other elevation, less than 15 volts. And then you come down through your next resistor. And now, when you get back to your starting point, you have to be at the same elevation again, right? You can't go on a hiking trail, end up at the same place you started, and be at a different elevation. You have to be back where you started. It's the same with current in a circuit. So let's see if we can solve this using Ohm's law. The potential difference across resistor 1 is equal to its current times its resistance. And the potential difference across resistor 2 is equal to its current times its resistance. And what do we know about these? We know that whatever current is coming into resistor 1 has to be the same current that goes into resistor 2 because there are no forks in the road. There are no branches for the current to split and take another path. All the current that goes through 1 has to go through 2. So I1 and I2 must be the same here. I'm just going to call it I from now on. What else do we know? We know that the potential difference across the whole thing, delta V1 plus delta V2, has to equal 15 volts. R2 is connected right here to 0 volts. And R1 is connected up here to 15 volts. So if we ignore this middle patch, we know that the voltage drop across R1 plus the voltage drop across R2 has to be the full 15 volts. We're not sure exactly what this intermediate voltage is, but we know the total has to be 15. So let's do a little algebra. Delta V1, I'm going to substitute in I1 R1, and I1 I'm just going to call I. And for delta V2, I'm going to substitute in I2 R2, but remember the I's are all the same. And what do I get? I times R1 plus R2 is 15 volts. I times 30 is 15 volts. I is equal to 0.5 amps. So everywhere in this circuit, the current is the same because there's no place for it to go. It has to just keep going around clockwise in this circuit.